Hello, we are back for the second clips, of the review of the ordinary differential equation, that is used to apply to solve to derive general solution of some physical problem, okay. So we can continue to the third example of actually, all the technique I mentioned to you again that we use the technique from the previous course of ordinary differential equation that you studied last semester. Okay, the third example here, is what we call the RLC AC circuit, alternate current circuit. Okay, from the previous example, we only have R and L system. Okay, the leading to the first order system. Okay, suppose we add one more capacitor unit, for the circuit. Okay, and the problems look pretty much the same. Okay, and we want to find the relationship between the input of the e t function. Okay, and for a given RLC lambda system. Okay, how the with the assumption of et, the function et. Okay, so what is the resulting function of it? Okay, this is also another classic from the physics governing equation. Okay, certainly we use the Kirchhoff voltage law again. Okay, and this one we add for more easier notation that we add what we call the d operator. Okay, the capital D operator as d by dt. Okay, actually, in for the if you study in electrical engineering class, that you might substitute this the d operator by j omega for sinusoidal source. Okay, et, which means that et is a sine omega t or a time cos omega t. Okay, and the response of d by dt. Okay, when changing to the frequency domain, you can substitute by j. J actually is a square root minus 1, the same as I notation used in complex number analysis. But in electrical engineering, since the I notation is used as a current, so they change the I notation for the mathematics of square root minus 1 to j. Okay. Uh, Now, the governing equation of KVL, certainly the voltage drop across these two poles, is according to the direction of the current. Okay, you have I time R, so which is Ohm's law. Okay, and certainly L di by dt, and since we substitute d by dt by capital D is L time d. Okay, and d by di by dt, this one. Okay, I move I to the separate multiplication term here. Okay, since all the term need to multiply by I. Okay, the last part is a capacitor here. Actually, the voltage that cross across the any capacitor, is simply 1 over c integration of it dt. Okay, but what's the integration mean related to the differentiation? Actually, as you might know from basic calculus, is that integration is the inverse of the derivative. Okay, which mean that the inverse is mean that if d is the derivative, 1 over d, is the inverse. Okay, which mean that d times 1 over d is equal to 1. Okay, this is the inverse of the derivative. So the integration is substituted by 1 over d. Okay, and c is that the voltage across c is a 1 over c. Okay, integration for all it dt. Okay, so this one is a 1 over dc here. The 1 over d times c is a representation of that relationship here. Okay, so this three part is a voltage drop for each element, in the circuit. Okay, all together with the direction of I from Kirchhoff voltage law need to be equal to the voltage across these two poles. okay, which is et, the function of et. Okay, so now you can see that if we trying to arrange this term, you can get this relationship. It's a little bit tricky if you, okay, let's just say that if I use d times c, okay, multiply on both sides. Okay, if d times c multiplied by both sides, okay, the right hand side become d times c, which becomes c d e t by dt here, okay, because you use c times this dc here, okay, multiplied by both sides. So the right hand side become c, okay, det become the derivative of det, function et by dt. Okay, for the left hand side, okay, the dc, okay, cancel this term, which resulting to it here, the last term here, since you have dc multiplied on both sides. The second term become the first term here, because you have dc here because L times c, right? And d times d become d square. D square become the second order of the derivative here. Okay, this is the second term become this term. Since you have dc multiplied by both sides, okay. And the first term become the middle term here. Okay, you have dc become rc and di by dt here. Okay. So the trick is only that you use d operator times c, okay, multiply on both sides, and then substituting d by dt. Okay, you get this second order differential equation. Since again we still stick with the lambda model, which means that RLC does not change over time. Okay, so but actually if it's changed over time, the problem become more difficult to derive for general solution. Okay, so this is another second order linear system, well known. Okay, so the problem is for the initial value problem here is that given, okay, et here, okay, given the voltage source over here, okay, with two initial condition. Why we need two initial condition? Because it's second order differential equation. You have two constant value for the complementary solution that at the end you need to derive and find the relationship and find the it once t start to be greater than 0. Okay, because when t is equal to 0, you already have the initial condition here. Okay, so this one is a similar, just extend the first example to be similar with the second example. Second example is purely the second law of Newton here. Okay, so we're going to start with analyzing the problem here. First, you know that the general solution of IT have to be equal to complementary solution plus particular solution. And the characteristic equation, certainly you go back here, okay, you know that this one have to be substituted by s squared because second order. This one di by t by dt is substituted by s, okay, and it is only, the coefficient multiply it is only to 1, and it is s to the 0, which is equal to 1. So the characteristic equation become LC s squared plus RCS plus 1. Okay, you can look at here, LC s squared plus RCS plus 1. Okay, plus 1. Because this, since di by dt is s, just it is only s to the 0, it says equal to 1. So this is the characteristic equation, is purely the quadratic equation. For general quadratic equation, you can easily derive, okay, to get this type of root, okay, s, suppose as square, because as over here, you can say s equal to the middle term. You remember ax squared plus bx plus c equal to 0? Okay, you get the root of x is minus b plus minus square root b squared minus 4 times ac divided by 2 times a. Okay, that's what we did here. Okay, so the b term is here, so s equal to minus r times c. Okay, this means plus or minus, okay, the middle term here, okay, square minus 4 times ac, 4, okay, 4 times this Since this is 1, okay, 1 times LC, 4 LC. Divided by 2A, 2 times A, which is this, according this, at this moment is L times C, okay. So we just try to separate the part because C, okay, on this can cancel each other, okay. And this C and C, okay. Okay, so you the first term is only minus R over 2 times L, okay, and you get plus and minus, you have 2 root, okay. You put 2LC in the root, so it become 4 times L squared times C squared, okay. So, okay, 4, so when you move it in, it become 4, okay. So the first term become R squared divided by 2L, okay, all square. Because C square cancel each other when you put it in the square root, okay. So remaining is R divided by R square divided by 4 times L square, okay. So and with 2, which is 2L square, okay. So you can put this term together, and 4LC here, okay. You when you put it in there, okay, 4 cancel each other, okay. LC and LC square become 1 over L times C. So there's 2 root here depend on R, L, and C according to the parameter of the problem. Okay, and in this case there are 3 possible cases that can happen here. Okay, the first case is that if you have R divided by 2 times L altogether square is greater than 1 over LC. In this case, you can have positive value within the root. So therefore, you end up having 2 root, okay, 2 real root, okay, real values of the root value. Okay, since the value in size is always a positive value. So the first one is plus this square root, and the second one is minus this square root. So you get 2 real roots. Okay, why this case is important? Because the characteristic of ICT depend on the kind of the structure of the root here. Okay, and also this is the basic knowledge that you should know from the previous class. The second one is that if R divided by 2 times L altogether square equal to 1 over LC, which means that this is square root of 0. Therefore, you have 2 repeated root, okay, which is only this term, minus R over 2 times L. And the third case is that if the value within the square root is a negative value. If it's a negative value, it's become the what we call the complex conjugate root. Suppose j is equal to square root minus 1. You end up having what we call the 2 complex, the root become what we call the 2 complex value, and have a property what we call the complex conjugate root, which means that the real part is the same, the imaginary part is the same except the sign. The first one is a plus, the second one is minus. Okay, so in each case, okay, leading to okay different type of complementary solution. Okay, for the real root solution, okay, it's very easy. You can extend from the first order system. You have constant times exponential function of that root times the domain, which is t now. So this one, the first root, the second one is the second root. So this is obvious for the first one. But for the repeated root, okay, as you might know from the second example, the first, because s1 is equal to s2, s of 2, which is s of 0. The first term is just the same, c1, exponential function of s of 0 times t. But the second term, okay, you need to add the domain t to multiply the constant here, c sub 2 times t e to the s0 times t. This is according to the rules, okay, mainly from the ODE, solving ODE procedure. The third one, okay, become a little bit more tricky because you have a complex conjugate. In this case, you have a real part, we call A, and the imaginary part is here. Okay, and the imaginary part is only excluding the j term, square root minus 1. Okay, so you might say that you have a 2 root in the form of a plus or minus j times b, a plus and minus j times b. So you put it in this form. Okay, it's become like a sinusoidal system with exponent component multiply. Okay. And you see that since RNL and RLC is a positive value, you can see that A is a negative value. And when A is negative value, you make sure that when t approaching infinity, this term is vanished. This term becomes 0. Okay? So this one just putting in the formula to the situation that we are trying to derive for the solution. Okay? And again, okay, suppose that we get ET, okay, the input function here, okay, the voltage function over here, as a R order polynomial, okay. You end up here, okay, as you observe from example 2, that since in this case we have a zero order term on the left hand side, IT, we have zero order term. So it's similar to the very first example that I particular solution here, we have a similar formula, but just a different coefficient because it's the unit on left hand side and of the function of I and E is a different one. So you need some transfer unit from A0, A sub 1, A sub 2, A sub bar to B sub 0, B sub 1, B sub 2 up to B sub bar. And again, how you find this relationship? We go back to the basics, things that we studied before. We comparing coefficients term to term from left hand side and right side for each term, for each additive term of the polynomial function. Okay, since the left hand side over here, okay, is differential equation, so you need to put the formula of IPT, okay, in the form, and then substitute, rearrange the term left hand side and comparing. Don't forget that the right hand side is not quite obvious also, okay, because the right hand side is ET here, and then we make very interesting here, okay. Let's look here, okay. Because for det by dt is become the right hand side become only r minus 1. Okay, r minus 1. Okay, let's look at the IPT over here. Okay, it's become the order r. Okay, and you need to find the general form for the first order and second order. This is the basic calculus. Okay, just substitute because the first order b0 vanish or the term b1t, okay, find derivative because which corresponding to t, it become b sub 1. This one become 2 times b sub 2 and so on up to r times b sub r. And this is the second order term, okay, second order term. You can see that b sub 1 vanish, only this one become 2 times b2 and this one 3, where the original one you have 3b3, but when you try to find the derivative of t square become 3 times 2b33. No, okay, and the fourth term and up to the r term here. Then you put on the substitution here for the left hand side. Okay, the left hand side is LC, so this is the second derivative, okay, plus RC, this is the first derivative, and this is the term of the zero order derivative equal to C times this one. This one is dEt by dt. Okay, so this term is coming from the put this, okay, all of this, okay, to the original equation here by using it, substitute it by I sub pt. Okay, you get this one of substitution, and then you can compare the coefficients. Okay, let's look at the constant term first, the term that have no multiplication with any t or t square up to t square. You have 2 times LC. Okay, you're going to 2 times 1, okay, to LC. Okay, and the second term is r times c, okay, times 1, okay, times b1, and then plus b0 equal to this one, c times 1, okay, times a1. This one is a constant term, that, and the term that multiply to t is over here is lc times 3 times 2, okay, and then b3, b sub 3. Okay, this one is a constant term that multiply to t. The second term is RC times 2, RC times 2, B sub 2, okay, times T. And then the third one is a plus that B sub 1, okay, B sub 1. And the right hand side is 2 times c times a sub 2. Okay, you start to see the trend. Okay, so it's very easy for the t square term. Okay, you get 4. This one 2 times 1, 3 times 2. This one 4 times 3. 4 times 3, b sub b2 dt. This one become b sub 4. And then for the second term rc, because 1 b1 2 b2, this one become 3 b3. Okay, and for the last term is always constant. Okay, plus t2 is a b2, and the right hand side becomes c times 3 times a sub 3. So you can see that the trend is that always LC, okay, multiply something, but the term is become 2, 3, 4, up to the last term you get r minus 1 times r minus 2. And the final one, r minus 1 increase to 1, r minus 2 increase to r minus 1. This one is almost not the end. The end is the last. This one up to the term r minus 2. No, t to the r minus 2. Because you observe here LC times r to the r minus 1. This is the last term. Time b sub r. Okay. Okay, this is t to the r plus minus 2. For this one, the rc, t r minus 2 become r minus 1. This because t to the r minus 1 become r br. So t to the r minus 2 become r minus 1 times br. Okay, br minus 1. And then you get constant LC multiply for every term here. And then the last term is really a constant b0, b1, b2 up to b to the r minus 2. Have to be the right hand side will be equal to c times t to the r minus 2 become r minus 1. Okay, because the r minus 1 will become r to the times ar. So t to the r minus 2 become r minus 1 times c, okay, times a r minus 1. So this is the last equation. But for the term of r minus 1 here, t to the r minus 1, the first term is vanished. They don't have any multiplication to the t to the r minus 1. Just the second term, you have rc times r br, rc times r br. Okay, and then the last term plus br minus 1, the term before the last term here. Okay, have to be equal to c times r minus c times r, this one r minus 1, right? So because we found the first derivative here, c times r to the ar. Okay, I. But for the last term, you can see that br here. This is the only term from the left hand side that have b sub r times t to the r. Okay, but the right hand side have nothing multiplied to t to the r. Therefore, b sub r is equal to 0. Okay, so now you know b sub r is 0. Okay, you can start back substitution in a similar fashion as we did on the second example. Okay, you have to look at the relationship, and then when you know b sub r here, okay, you know b sub r here, this term is 0, the equation before, you can get b sub r minus 1. Okay, so which is exactly equal to c times r times a sub r. This, which is this one, b sub r minus. Once you know b sub r minus 1, you can substitute back. Okay, for the next, in this one, you know b sub r is 0. You know b sub r minus 1, you just move this to the right hand side. You get b sub r minus 2. B sub r is in this form. But b sub r, but you know that b sub r minus 1 is equal to here, to rc a sub r. So you can substitute b sub r minus 1 over here. But it's gonna make term even longer. But you know that it's kind of in mathematics we call this a recurrent relationship. This means that you get one value leading to the other value in sequence. Okay, you get b sub r minus 1 here. You substitute b sub r minus 1 over here. Okay, you get b sub r minus 2. Okay, when you get b sub r minus 2, you substitute here b sub r and b sub r minus 1 substitute here, you get b sub r minus 3, and so on up to the first term. Okay, also we look at this in the trend, the trend of the function here. The first term you get r times c, okay, a sub r. Second term you get r reduced to r minus 1, c still remain, but a instead of ar become a sub r minus 1. Okay, The third term r minus 1 become r minus 2, and this c a sub r minus 1 become a sub r minus 2. Okay, the next term become r minus 2 become r minus 3c. Okay, a sub r minus 2 become a sub r minus 3. Okay, so with the second term, the complete term will start at b sub r minus 3. Over here, you get r minus 2 times c, a sub r minus 2, minus here. We should start here with this equation. B sub r is 0, so you b sub r minus 1 is obvious, okay? B sub r minus 2, you have two terms. But once b sub r is 0, is no more. B sub r minus 1 have exists some non-negative value. So at b sub r minus c, when you move these two terms to the left hand side and rearrange the term, the remaining equation become, the index just keep rolling in a similar fashion up to the b sub 0 value. Okay, so this is what we did. We just arranged the term from b sub r minus 1, b sub r minus 2, and then start b sub r minus 3, you get here. R minus 2 here, okay, and then I just take out the common value, r minus 2 times c, okay, r minus 2 times, put it in here. So the first term become a sub r minus 2 minus this one, r minus 2 times c come out, the remaining become r times b r minus 2. This one, r minus 1 c, take it out, the remaining term become r minus 1 times l, okay, times b r minus 1. Okay, so this is the first to generate. So when you change from r minus 3 to r minus 4, r minus 2 become r minus 3, reduced by 1 unit. C is the same. A sub r minus 2 become a sub r minus 3, reduced by 1 unit. Minus r the same. B sub r minus 2 become b sub r minus 3. And r minus 1 here, change to r minus 2, reduced by 1 unit. L is the same. B sub r minus 1 become b sub r minus 2. You can see that once this reduced by 1 unit, this one reduced by 1 unit for both index and the constant that multiply. And it keep moving on to the toward the end with b sub 2, this one start to reduce up to 1 point. You can see that r minus 4 is less than r minus 3 by 1 unit. So when b sub r minus 4 reduced to b sub 2, this one have to be the term that multiplies c have to be greater than the index 2 by 1 unit. You see that? R minus 4, R minus 3, and R minus. So this become 3 times c. Okay, certainly. And you can see that this one ar minus 4 and b sub r minus 4, this one a sub r minus 3. If this is b sub 2, this become a sub 3 because r minus 3 is greater than r minus 4 by 1 unit. So this one, when you reduce to 2, this one greater by 1 unit is 3. Minus r is the same, but b sub r minus 3 the same. This one a sub 3, this one b sub 3. This one r minus 2. R minus 2 is greater than r minus 4 by 2 units. So when you reduce r minus 4 to 2 units, this one have reducing down to 4 units. Still 4 minus 2 is greater than 2 by 2 units. And L is the same. And b sub r minus 2. So this one have to be b4 since this is b2. Right? 4 is greater than 2 by 1 unit usually. And then when move to b1, this one become 2c. 3 to 2, okay, a sub 3 to a sub 2, b sub 3 to b sub 2, and b sub 4 to b sub 3, up to the unit of b sub 0 here. Okay, so now you can say that, okay, the general formula of IT is I complementary solution plus particular solution. And you can see that particular solution, we only have an r minus 1 polynomial function order. Okay, polynomial function with order only r minus 1 because we already proved here that b sub r is equal to 0. Okay. So this is and you can find b sub 0 up to b sub r minus 1 using this relationship. Okay, because this one once you know the index of a small r, and then you know the value of a0 up to a sub 1, a sub 2 up to a sub r, and you know RLC value, you can substitute using this recurrent relationship. Okay, but the derivation is not completed yet because I sub ct, okay, for the complementary solution, we have 3 cases. to verify. Okay, as you might recall that in here. Okay, you have three situation, and three situation coming from this type of case. Okay, the situation you have two real roots, two repeated root, or you have complex conjugate root. Okay, so the next step is to try for all three cases you need to derive for the general formula for the constant value. So okay, for case one, okay, given the initial condition I0 equal to the first order at time 0, okay, of I is equal to 0, or so you just use I0 here, just put in here I0, okay, 0, or the only remaining term is only b sub 0, okay, you get b sub 0. But the first term for case 1, you know that in general form is here. You can see I0, E exponent all have the power of 0, so it becomes C1 plus C2. Okay, well, in case 1 over here, you get C sub 1 plus C sub 2 plus B sub 0 equal to 0. So for the first derivative, okay, the first derivative is you need to find the first derivative here, okay, or the case 1. The first derivative becomes C sub 1 S1 e to the S1 t plus C2 times S sub 2 e to the S2 t when you find the derivative of ICT according to dt here. So you instead of you have C sub 1 to C sub 2 alone, like you have S sub 1 and S sub 2 multiplied to C sub 1 to C sub 2 respectively. So that's why this one, when you substitute t equal to 0, the constant becomes S sub 1 C1, S sub 2 C2. And you only have B1 remaining because when you find the derivative here, okay, for the IPT, the particular solution, B sub 0 is vanished, B sub 1 become constant. But the other terms still have t multiply the coefficient. So when you substitute t equal to 0, they all vanish also. So only B sub 1 left here. Okay, so this is how you get these two equations. And with these two equations, you get two equations. You get, and with two variables, you have two constant values, C sub 1 and C sub 2. Okay, with the right hand side, B sub 0 and B sub 1. So this is a simple solving of equation that first, okay, you get the first equation, you write C sub 1 in terms of C sub 2. C sub 1 equal to minus C sub 2 plus B sub 0. And then you put C sub 1 in terms of B C sub 2 in the second equation to derive from C sub 2. Okay, so the second equation S sub 1, okay, C sub 1 is using this in terms of C sub 2 here, substitute it here. And then the second equation, you only have C sub 2 left, so you rearrange the term. Very straightforward, and you get this relationship of C sub 2. And then you put this C sub 2 back to the first equation to derive from C sub 1. Okay, so this is a quite straightforward derivation for the general form of C sub 1 is C sub 2. Okay, so in the next step, what we are doing is that we using the similar analysis for case 2 and case 3. Okay, in case 2, okay, you might remember we have this case. Okay, so you can see that when I0, okay, when you substitute is 0, okay, you know that IPT only B0 left, but this term when you substitute 0, C sub 2 is vanished, so only C sub 1. So in case 2, you can see that very easy, C sub 2 is vanished because it's multiplied by t, so when substitute, so you get C sub 1 is equal to minus B sub 0. Okay, where's B sub 0 coming from? Because here, okay, when you substitute I0, okay, all the remaining are vanish except B sub 0 for the IP function of t. Okay, oh sorry, okay, over here. And then after this you get I pi t. Okay, this is the first order derivative of it in case 2. Case 2, you know the first term is C sub 1 e to the exponent function of S0t. So when you find the derivative, it's only move S sub 0 here. So C1 S sub 0, similar to when you have the unrepeated root here. But the second term is a little bit more tricky because The second term is a multiplication term of function of t. You can hear. So because when you find the derivative is not obvious, just like the previous case, because you have t times e s0t. So this one is you need to use a multiplication function derivative. Like you remember derivative of u times v is equal to u dv minus u dv plus v du. Okay, something like that. Okay, this one also get these two terms. Okay, so C2 is a constant value. Okay, okay. The first term is that u, okay, t is still keep there, but when you find derivative of e to the s0 t, you get s0 e s of 0 e exponent of s of 0 t. So u times v, remember that these two terms, okay, t. You keep t, okay, u dv is at s0, you dip this term, you get this plus v. This one is the second term. But since you find derivative of t is equal to 1, yeah, so this one is it's not that obvious, just like a previous example. And then you substitute, okay, this one also the term of the derivative for the particular solution part. Okay, this is a particular solution part. Okay, we did it so many times about here. Okay, therefore when you substitute t is equal to 0 here, okay, so the first term become c sub 1 s0 or s0 c sub 1. The second term, okay, the first term when t0 is vanished, but for the second term with c sub 0 you get c sub 2 remaining. And then this one, certainly b sub 0 vanish once you find derivative, only b sub 1 left. Okay, so we can use the first one here. You already, the first condition that you find c sub 1 is equal to minus b sub 0 here. So you get b sub 0, okay, and over here, okay, to substitute here, okay, and you get c sub 2 here. By moving here, plus b1 become minus b1, and then minus b0, okay, you substitute this, and when you move to the right hand side, okay, this one become minus, but c sub 1 is minus b0, it become positive value. So c sub 2 is equal to s sub 0, b sub 0 minus b sub 1. Okay, so this is the second case, okay. And certainly b sub 0, b sub 1, okay, can be found using this recurrent relationship, okay. Okay. This one. Okay. So next is the third case over here, okay. You get I, okay, 0, okay. Obvious the same case. We have to go back and look at the general form here, okay. When you have I as 0, certainly this one e to the 0 is 1, and then sine 0 is 0, the second term is vanished, but the first term cos 0 is 1. You only have c sub 1 for the ICT. Okay, that's how you get this one, only c sub 1. But for the second term, for the second part of the here, okay, when you substitute t0, you only have b0 left, okay, all the remaining term are vanished for the IPT, okay. Oh, I'll move here. So you get this one, c sub 1. Certainly very similar to the second case, you get c sub 1 first. And in order to get c sub 2, it's a little bit more complicated because now you have two multiplication functions. Then you need to find the derivative here because e to the at cos bt and e to the at sin bt, c1, c2 is constant. So the same, you use in u dv plus v du, okay, from the basic calculus here. I'm not gonna explain much here, but you can see that, okay, when you find the first derivative, c sub 1, c sub 2 constant, but the inside is u dv plus v du. You take e to the at is u, v is cos bt, okay, so the first term is e to the at, and you find the derivative of cos bt is become the derivative of cos is minus sine bt, and then you find the derivative inside of sine is bt by dt, you get b here, okay, plus Okay, the original term is AE to the AT. Okay, this one cos BT is the original one. V du is an E to the AT. When you find derivative, become AE to the AT. Similar fashion to the second term. Okay, but you change to E to the AT times sine times cos BT become E to the AT times sine BT. So when it's sine, there's no you find derivative of sine become cos. Okay, and then all positive value here. Okay, and then you substitute t is equal to 0. When t is equal to 0, the time with sine is all 0. Okay, with cos become 1 and e to the 0 become 1. So this one and you need to make sure that your particular solution is in the second order form. So when you substitute this to at time 0, you get this. The first term become a times c1. The second term become b times c2, and the remaining part of the particular solution is similar in all case with b sub 1 equal to 0. Now you already found c sub 1 is minus b sub 0. You substitute that to here, then and rearrange the term, you get the solution of c sub 2 here in general form. So you get c sub 1 and c sub 2 in general form. Okay? So you can see now that how you derive the general solution of a physical system, both electrical and basic electrical and basic mechanics. Okay? And we still stick with the classical. We want the first order system and second order system. Okay, up to this point, okay, I think you should be able to do some homework here. Okay, to make sure that you understand. Okay, and we have a couple of problems that refer to what we already explained before. Okay, just like the first problem here of the from exercise 3. Okay, the latest example that we when we start to explain in this script, this one we only did what we call the initial value problem. Remember in exercise 2, okay, we have boundary value problem here. We derive the general solution for the boundary value problem. Okay, but in case of the here, okay, we only did the initial value problem, but we haven't done here the result for the boundary value condition, that when you given time, okay, within the horizon of 0 up to capital T, and then you have initial solution for a given and then I sub 0, I at t equal to 0, and the current at uh, the period, the horizon period, capital T, and after t is greater than capital T, there's no IT. The switch is on. The switch is off. Okay, it's not. It's become open circuit, just like what we explained before. Okay, so this is the first uh, homework. Okay, for you to exercising. Okay, what you have been studied so far after 3 examples. The second problem, okay, become is extended from the second example. Remember, in second example, we only have mass and we only have apply the force. Okay, so therefore some displacement. We adding two element, mechanical element. The first one we call the spring, okay, with a constant, a classical spring with constant K. The second one we call the damper or choke system with a constant C. Okay, and this is already a well-known governing equation in physics that you might remember that by second law of by second law of Newton. Okay, you have m times, okay, the second order of displacement, which is the acceleration. The first term is the second law. Okay, and you know the force that caused by spring is well known. It's similar to Ohm's law in electrical engineering, that V equal to IR, F is equal to K times X. Okay, so this is a zero order, okay, relationship between force and displacement. Once you have a mechanical element called spring, okay, to balance, okay, the displacement. Okay, so F is equal to Kx. So there are two more elements, okay, to resist the movement forced by f sub t, function ft here. Okay, you have kx, okay, which is caused by spring, k with constant k. You have second order, okay, of uh, second mass motion from Newton's, okay, m time. But for the choke and damper is a mechanical element that you can see that you have zero element here on spring, and you have a mass element which is a second order system. So you need one first order system, just like when you study in the example of mechanical system. In a mechanical system, you can see that, oh, no, in electrical system, you can see that L is a first order, okay? But C is a minus one order. Called minus one is because it's 1 over D. You remember that? Instead of D, which is D by dt, it's only 1 over D. So it becomes D inverse, so minus 1 order. And that caused the problem that to rearrange the term, and that make the system from the third example become what we call the second order system. But for mechanical system, we just add this element called damper or choke, okay, which have some relationship pretty similar to the inductance there with constant L, okay, with the after being uh, after the current passed by, okay, yeah, that's what the resisted voltage that generate to cross across the that element, okay. But in this one we use C here, okay, C, and this one dxt by dt, the first order. That's the force cause, okay. Once you apply force here, there's some resisted force over here. So for the first law of Newton, okay, the balance of force, okay. So once you apply a force function here, okay, the three element that resist the movement, okay, that cause the movement of xt here, okay. One is the mass, second one is the spring k, the third one is the damper c, okay, here. And also, okay, once you get this system, okay, so this one just change the notation a little bit, but you can use and apply directly the what we did in the third example here, that if ft is what we call the polynomial order r, you want to derive the general form of displacement xt, okay, when x0 and x, so this become the initial condition problem, okay. So we want to go back and review third example again and try to derive the general solution here. And to make the thing a little bit more challenging for you, that because all the input function or the right hand side function that we've been using in all cases is a polynomial order r, okay. But we're going to change a little bit for this math problem after you finish 2.1 and 2.2, okay. If the force function is a kind of a combination of several sinusoidal, a sub j cos omega j times t plus b sub j sine omega j times t, okay, and you have a m term, okay, in general j is equal 1 to m, okay, there's m term here, okay. Just try to think a little bit. If ft, the right hand side become what we call the uh, many technical term, we call that, some them call transcendental, okay, transcendental form, some them so, and in electrical engineering you're familiar with sinusoidal form, okay. uh, and we have so many way to represent this type of function, okay. So it becomes the many a combination of several sinusoidal input, and sinusoidal input in mechanics you can refer as a vibration, it's a vibration, the force that giving you like up and down, the vibrate, okay. And so in this form you have so many vibrating curve, okay, for force, okay, that can be applied to different type of frequency, omega j, okay, omega is equal to 2 times 2 times pi times frequency, right? So several force with several frequency of vibration, okay, have been applied. Okay, so and we want to know, okay, the general solution here. Okay, repeat 2.1, okay, with initial value problem is the force function change to the right hand side change to this form. I haven't done this for you because all the problem that we did before is all polynomial order R. But this one is kind of challenging for you that, okay, this is a new thing you unseen. You first see it, but how you going to do it? You can find it in the internet, in the several by Google and try to find how we're going to uh, make sure that this problem can be solved appropriately. Okay? And the third example here is become a little bit challenging for you because we add more element to the third example. Like in this one, you have two resistor, okay, R sub 1 and R sub 2, and you have two inductance, L sub 1 with L sub 1 and L sub, and you have only one capacitor here, okay. And this one, you not only need the requirement of mathematics, you also need the requirement of using the basic physics and basic electrical engineering knowledge to derive what we call the differential corresponding differential equation here first. And we have some hint, okay, for you that the resulting system here is going to be what we call the third order system, okay. uh, let's try out how it's going to look like, okay. And when you have third order system, you need three initial condition here. We have three initial condition here, okay. And therefore you need to find the root of a cubic equation. Remember that the second order you need to find the root for the quadratic equation. Third order become the corresponding characteristic equation or auxiliary equation become cubic equation that can have three possible root, okay. Okay, and then I gave you something to think about it, that you can find the root of the cubic equation from the Wikipedia by using a search term of cubic equation. Okay, and the fourth one is that you can go back and review from the first examples to the first three example, first order and to second order example, okay. And if you already know how to do this 2.2, okay, when you're changing the right hand side here, and when the right hand side function changing, this one is a little bit combination. Okay, you remember 2.2, you know how to do this, okay. The sinusoid, you already know how to deal with the polynomial function, but now you have to deal with the hybrid, all of them. You have both the right hand side. In the case of AC circuit, is become the voltage source ET, okay, and for the mechanic system become the force function. Okay, suppose your force function and your voltage source function is a hybrid of both R polynomial order R and also the m terms of the additive sinusoidal function. Okay. Suppose that you have both of this, okay, all together in all example, how the solution gonna come and look like. Okay, so you can just go back and refer and try to work in practice on thinking about this. Okay, I'm sure that you can find something, and if you still don't know, okay, just to do your best, try to do as much as you can first, and then we will try to review and help you a little bit to get out of all this question. Okay, so that wraps up the second part of my lecture, okay. And next time, okay, we're gonna move on to a little bit more complicated technique we call the higher order linear differential equation, because in the first up to this point we only deal with deriving the solution for only the first order system and the second order system. Okay, but in reality, the system, engineering system, is a very large system. It consists of several of these first order, second order, connecting to each other, okay, and that resulting the uh, kind of consequent relationship leading to a very large, and you can have a third order, just like we start from this homework problem number 3, that you can see that we become third order system. We can up to fourth order, fifth order, sixth order. You might wonder it can go up to 100 order or several thousand order. Okay, just think about this, that in electrical engineering, the when you're working on some equipment, just like your iPhone or your any other electronic device. Okay, the representative, the circuit representative of that system can be consist of 1,000 element of this. Okay, and how electrical engineer analyze this. Okay, if there's so many L and C happen, okay, when using the governing law of physics, okay, it's gonna end up having a much higher order system. Okay, so we're gonna touch a little bit that how this higher order keep increasing, and that how is this gonna make the problem more difficult and more, and in both case of initial value problem and boundary value problem. Okay, that will continue in the next script. Okay, so for this moment, okay, we're going to stop here, and hope you, okay, go back and review and try to work on the homework that I've been mentioned about. Okay, so okay, see you in the next script.